So we're slowly coming up to the best part, namely the part where we're about to run our gradient descent algorithm on our mean squared error cost function. But before we dive into the Python code and calculate in which direction our algorithm should move, we need to work out the slope of our cost function first, namely our gradient. And this is where I've got some great news for you, because we just have to apply some of the same calculus tricks that we've covered so far, and these partial derivatives that are coming up are really not that hard to figure out. So let's dive in. Now you'll recall that our mean squared error function looks like this. It's 1 over n times the sum of y minus y hat squared. So the actual values minus the predicted values squared, you sum them all up, and you take the average. But the thing is, since we're running a very simple linear regression on this with one variable only, namely x, our y hat actually takes the form theta 0 plus theta 1 times x. This is the linear regression model that we're using currently. It's got one variable and two parameters, theta 0 and theta 1. So what does this mean about our mean squared error? Well, if we take our equation and we simply substitute our model, our linear regression model, into this equation for y hat, then we get something like this. And by removing those parentheses, we can simplify this to the following form. Our mean squared error for this particular linear regression model actually looks like this. We've got 1 over n times the sum of y minus theta 0 minus theta 1 times x squared. But you know what? We can take this even further. Check it out. What we're going to do now is we're going to write out all the terms in this equation. So this is the opposite of simplifying it, but it's going to make calculating our partial derivatives a lot easier. We can figure out all the terms in this sum like so. Firstly, we can multiply out all the terms in this equation, and that means we get something like this. We get quite a few terms, starting with y squared. But of course, there's a few terms in this long list that we can combine, so we'd actually get something like this when we simplify it a little bit. Now, I know that that doesn't look very pretty, but the great thing about having the equation written out like this is that we can calculate our partial derivatives very, very easily. So what I want to do is I want to start this lesson out on a challenge. I would like you to get out pencil and paper and try to apply the power rule to the equation above, to our mean squared error equation, and take the partial derivative with respect to theta 0, so our intercept. I'll give you a few seconds to pause the video before I show you the solution. Ready? Here we go. Now, looking at this equation, the first thing you'll notice is that there are quite a few terms that don't depend on theta 0, namely y squared, 2 theta 1 xy, and theta 1 squared times x squared. For a partial derivative, these terms are treated as constants and they drop out of the equation. This is what we've talked about before. So what are we left with? Well, we're left with the following sum: minus 2y plus 2 times theta 0 plus 2 times theta 1 times x. And this is simply from applying the power rule that we covered in a previous lesson. Now, looking at this equation, we can simplify it a little bit to make it look a bit prettier. The first thing I'm going to do is I'm going to factor out the 2 that all these three terms in the sum have in common. In fact, I'm actually going to factor out a minus 2, and then I'm left with something like this. I've got minus 2 times y minus theta 0 minus theta 1. And then what I can do is I can simply move this constant outside of the sum. So our equation would actually look like this. And that's really it. That's the partial derivative with respect to theta 0. One thing that you might have noticed is that I've left out the little i's in the superscript in this derivation. And I'm going to put those back now for you. I left them out earlier because otherwise the notation would have just gotten too busy on the slide. So now that we've worked out the partial derivative with respect to our first parameter, we can work out the partial derivative with respect to our second parameter, namely theta 1. Once again, I'm going to pose this as a challenge to you because you've worked out this one. Working out the other one is very, very similar. You go through exactly the same steps, but you'll get a slightly different result. I'll give you a few seconds to pause the video and scribble this down with pencil and paper. Ready? Here's the solution. The equation that you get at the end when you go through all the steps and you simplify it will look something like this. It'll be very, very similar to the partial derivative with respect to theta 0, except that you're multiplying the entire thing by the x values at the end of the sum. And with these two equations in front of us, we can now add them to Jupyter Notebook. Once again, the first thing I'm going to do is add a section heading with some markdown and our LaTeX equations. This section heading I'm going to call partial derivatives of the mean squared error with respect to. Then I'm going to add a $sign, a backslash, and write theta underscore 0, and then another $sign, and $sign backslash theta underscore 1 $sign. Using the $signs, I'm including some LaTeX notation in line for our section heading, and it's going to look like this when I press Shift Enter. But let's add our partial derivatives in LaTeX notation as well. So I'm going to add two hashtags, two pound symbols, then two $signs, and write our fraction. So it's going to be backslash FRAC, pair of curly braces, and then another pair of curly braces. And within the first pair of curly braces, I'm going to write backslash partial MSE. And then in the second pair of curly braces, I'm going to write backslash partial backslash theta underscore 0. And that whole thing is going to be equal to, but before I add that bit, let's take a quick look what this looks like. So I'm going to add my two $signs at the end, press Shift Enter, and there I can see my fraction with the partial derivative symbols in front. Okay, so just so we have our equation in our Jupyter Notebook as well, let's write it out here together. So it's going to be minus, and then backslash, frac, curly braces, 2, curly braces, n, I'm going to put a space here, and then backslash, sum, underscore, curly braces, I equals 1, curly braces, carré, curly braces, n, and then backslash, big, open parentheses, y, carré, curly braces, and then inside parentheses I, minus, backslash, theta 0, minus, backslash, theta underscore 1, x, carré, curly braces, and then inside parentheses I. And then the last bit is going to be backslash, big, closing parenthesis. Let's see what this looks like. I'd say that's pretty spot on. I'm just going to click inside here and add the second one as well. This is the easy part. This is where we just copy what we've just written, paste it below, and then change this thing here to theta 1. And then at the end, we're going to add backslash, big open parentheses, x, carré, curly braces, parentheses, I, and then backslash, big, closing parenthesis. That's it. Now we've got our partial derivative equations displayed beautifully in Jupyter Notebook. So one thing that I'll note here is that, these partial derivatives are going to depend on what kind of equation we're using for y hat. At this point, we're using linear regression with one variable. So we substituted that in there, and then we derived our partial derivatives from that. If we had a different model, say linear regression with two variables or something that estimates our y hat a little differently, then we'd simply substitute that equation into our mean squared error, and then we can do the same derivation if we're so inclined. Because that mean squared error cost function lends itself very well to all sorts of regression problems. And it will adapt very, very well to all kinds of models as well. So having written out the partial derivatives in this form, we can create a function where we calculate the slopes of the parameters in Python code. So I'm going to add a little section heading here. I'm going to call it MSE and gradient descent. And then that Python function I'm going to add here. Now what I'm going to do is I'm going to create a function called grad. I'm going to say def grad, and I'm going to give it 3 inputs. I'm going to give it the x, the y values, and an array of thetas. And I'm going to say colon, and then inside the body of this function, I want to work out these 2 partial derivatives. So what are my inputs here? My inputs are the x values, so the data, the y values, again, this is also data, and then I have an array of theta parameters. These are the bits that we're actually optimizing in our gradient descent algorithm. This array is going to have theta 0 at index 0 and theta 1 at index 1. So this is going to be my function. The number of samples, so n, I can work out by saying n is equal to y dot size. This function is going to get a whole list of y values, and by calling y dot size, I can work out how many samples were given to this function. Now, as a challenge, can you create 2 variables, theta 0 underscore slope and theta 1 underscore slope? And what I want you to do is I want you to translate these LaTeX equations into Python code. I'll give you a few seconds to pause the video and work this out. Ready? Here's the solution. So theta 0 underscore slope is going to be equal to minus 2 divided by n times the sum of y minus thetas square brackets 0 minus thetas square brackets 1 times x. So we're expecting that this function will receive an array of theta parameters, and I'll have the theta 0 at index 0. So this is what we're using here, and we have theta 1 at index 1. So this is what we're using here. Now working out our theta 1 underscore slope is going to be trivial, because I can just copy this, change the name here, and then simply add another set of parentheses to our sum and multiply the whole thing by x again. And that way I can capture this term in the equation here. So that's really it. The only thing left to do is output these values. And we're going to output this stuff as an array. I'll show you 3 ways we can do this as a little bit of a review. So we can write return np.array, open parentheses, square brackets, theta 0 underscore slope. And because this is an array as well, we just have to pull out the first value of it. And then write a comma, and then theta 1 underscore slope. And then grab the first value of that as well. Now, this is one way you can do it. We've calculated these 2 things separately, so we can combine them into an array like so. But I'm going to comment this out and show you a second way. So we can also return np.append, open parentheses. The first argument is going to be our theta 0 underscore slope, and then our second argument is going to be theta 1 underscore slope. So this is a second way we can do it. We can append this array to this one and return that as well. So that way we can combine these 2 pieces of data that were calculated separately and append them to each other. The last way I'm going to show you is with the concatenate function. So this is also from NumPy. That'll be numpy.concatenate parentheses, and then another set of parentheses where we're going to supply theta 0 underscore slope, comma, theta 1 underscore slope. And then we just have to supply how we're going to concatenate it, namely along the rows. So axis equals 0. So these are 3 ways you can write the Python code to achieve the very same output. Now it's time to run our gradient descent and actually call this function. Let's hope I didn't make any typos. So let's do that now. This is where the rubber meets the road, as they say. I'm going to set my multiplier to 0.01. And I'm going to set my initial guesses. So my theta's equal to an NP array where our initial guesses are 2.9, comma 2.9, all in square brackets. And then our gradient descent is going to look like this. It's going to be 4i in range. We're going to run this 1,000 times, colon, and then in the body of our for loop, we're going to have some very terse Python code that calculates our gradient and then updates our thetas array all in one go. It's going to be thetas is equal to thetas minus multiplier times grad. This is where we're calling our function. And now we have to supply our data, right? X underscore 5, comma, Y underscore 5. This was the data that we generated earlier. And then last input is going to be our thetas array. Just like that. After our loop has run, we can print out the results. So this is where we can check if our thing actually works. And I'm going to find out if I made any typos along the way. So I'm going to print, and I'm going to say the min occurs at theta 0, colon, comma, and this is going to be thetas square brackets 0, because that's where our intercept is going to live. It's going to live at index 0, first value in our thetas array. And let's print out the minimum at theta 1 as well. So it's gonna, that one's going to be in a print statement, min occurs at theta 1, and then comma thetas square brackets 1. And finally, we're going to print out our mean squared error. So we're going to use that MSE function that we created earlier. So I'm going to say print MSE is colon, comma, MSE. This is our function call, parentheses, and then we have to supply 2 things here, remember? Y underscore 5, so the actual Y values, and then Y hat. What's Y hat? Well, after our loop runs, it's going to be thetas square brackets 0 plus thetas square brackets 1 times our x data. So x underscore 5. All right, so we've just written a whole bunch of code without having tested it in a little while. Let's see if it works. I'm going to hit Shift Enter now, and I'm pleasantly surprised. We get, after 1,000 iterations, we get a theta 0 value of 0.85 and a theta 1 value of 0.122 and a mean squared error of 0.95 approximately. And this very much ties out with all the calculations we've done previously. So we've definitely done this correctly. We've worked out the partial derivatives of our cost function, and then we've run our gradient descent algorithm, and this gradient descent algorithm started pretty far off, started at 2.9 for both our theta 0 and our theta 1 values, and then in that for loop, having run 1,000 times, it converged on the values that minimized the mean squared error, that minimized our cost function. So this is brilliant. Now all that's left to do is to plot it.